Professor Sarawagi. Welcome. Professor Sunita Sarawagi is the winner of our Infosys Prize in Engineering and Computer Sciences 2019. She studies and queries a host of unstructured data, but let me not oversimplify it. Let's hear what she has to say.
Okay, thanks. So, machine learning. So, but this work for which I got the award is on old style machine learning, which was statistical machine learning, where we still depended a lot on humans to do feature engineering. And I worked on statistical machine learning for information extraction from unstructured text. So, I'm particularly focused on the kind of unstructured text that comes out of flattening structured data. So what I mean by that, so suppose you have address. The address is a text string, but there is structure in that address which a human can decipher, but machines find it difficult. Other examples, citations, lists and tables on the web. And to humans, the structure in such text is obvious. For example, if you see an address like this, it's very easy for humans to decode structures such as, the first part is house number, building name, area, city, pin, and so forth. When I see a citation string, you can easily break it up into its structured elements. Even for arbitrary list that you see on the web, suppose if I present to you a list like this, it will take you just a second to figure out that the parts in red refers to university names and the part in green refers to locations, although we have not really trained an explicit model for this. So for humans, even though the information is present as undifferentiated sequence of words, we can decipher the structure effortlessly. But we are not interested in just depending on humans. We would like to go for large-scale processing of information, particularly when you think of applications like web search, and we would like to automate, like companies like Amazons and Flipkarts of the world would like to automatically understand address so that they can do geocoding. We want to detect duplicates. So one of the reasons why I got into this task is because income tax department had this huge list of addresses, and they wanted to merge this list of addresses so that they could detect duplicates. Citations, every time you use Google Scholar or Semantic Scholar to find out how many citations your paper accumulated, you have to do such kind of structure deciphering and deduplication. And I'll soon talk about how structure extraction is essential for also answering factual queries on the web. So structure extraction is easy for humans but hard for machines because there are too many variant ways in which the same information can be expressed. Think of the number of ways, particularly if you live in India, in which your home address is mentioned. Okay? And this becomes even harder for open domain set of types like what you saw in the example of lists on the web. And early days, like, I'm talking about, say, late 1990s, there was this, genre of people who would be working on automatic wrapper induction. And there was a lot of work on, rule induction methods, which would be partly human supervised. But these did not generalize very well. And that's what led a bunch of us to invest in statistical machine learning, where we thought that since humans find it so easy to extract structure, let them provide a few examples, and then we will depend on machine learning algorithms to generalize over the different noisy variants of that structure, of that text. So my research has been on designing statistical machine learning algorithms, models, inference algorithms, training objectives for large-scale information extraction and integration. And broadly, I can partition my research in two categories. The first half of my research in this field has been when I considered the easier fixed domain setting, like when you pick a domain like address or citations, where the structure is known in advance, so you have labeled data which all has the same fixed structure but different variants of text string which encodes that structure, and then you design models to learn from such input. And then I went on to the more ambitious task of solving structure extraction task while doing online learning, while answering factual queries on web scale lists and tables. So I'll just give you a brief overview of my work in each of the two domains. So one of the centerpiece model for this information extraction tasks is conditional random fields. So this model was developed in CMU in 2001, where suppose if you are given an undifferentiated sequence of words like this, you would use a model which would first convert this text into tokens, like say in this sentence we have 8 tokens, and then the information extraction task just boils down to labeling each word in this sentence with one of the known structured types which you have declared in advance, because it's fixed domain. Okay? And there is exciting algorithmic work, inference challenges on how you would find the most likely labeling of a sentence and how to train the model. And CRFs were a big improvements over hidden Markov models because they did global conditioning. They produced very reliable uncertainty estimates. In fact, for example, HMMs did not, whereas CRFs did, and they were really kind of held high by the research community. But then a bunch of us came along, and we sort of tried to change the game by saying that we should not think of structure extraction as a sequence labeling task, but rather it should be considered a sequence segmentation task, so that you take a sentence and you segment it so that each segment refers to a structured entity. The advantage of doing that is that now if you have like a large dictionary of people names, titles, research titles and conference names, you can use those existing databases to provide features, because at that time we did not believe so much in deep learning or neural networks. So you're dependent on future feature engineering, and one very important feature was whether you find a match in an existing dictionary or not. So this work carried me in the early 2000s, so I had papers in ICML, NIPS, and all the top conferences in this area, and we applied it on various tasks like address cleaning. And address cleaning for Indian addresses is a totally different story from address cleaning for Western addresses. Indian addresses are not declarative specification of addresses. They are algorithms, right? So you have to, so that was fun. And then we worked on address extraction from citations, and we got improvement in accuracy. And then a big challenge we faced also was that the segmentation model was inherently quadratic, and we had fun coming up with inference algorithms. In fact, I'm proud of this solo paper I had in ICML 2006, where we figured out an inference algorithm which reduced the running time of sequence segmentation models from quadratic to almost linear, but of course it was dependent on the feature set. And so in practice it made a difference. Okay? So next we are going to switch gears and talk about a structure extraction tasks for the open domain web kind of setting. So let's consider a specific kind of queries. So these are queries like, say, a user types this kind of a sequence of keywords which say escape velocity Jupiter, or height of Mount Everest, or battery life of iPad. So the answer to these 3 queries is a number. Okay? So back when I did this work in 2013, if you asked these queries, say suppose if you asked for what is the escape velocity of Jupiter, you would get all Rahul Gandhi jokes, okay? Whereas, so essentially in the IR community, it's like you get back 10 blue links. Whereas what we would really like is a factual answer. So that was our goal. And now if you search, pose this query, this is the answer you get on Google, but that was not the case in 2013 when I worked on this problem. So, so our point was that, for these numerical queries, you're best off looking for answers on the millions of organically created web tables, instead of hunting for such answers from documents. Because whenever people have statistical or numerical information, we sort of very naturally we try to represent them as tables. And at that time, tables were largely ignored by most of the large search companies in answering such queries. So, so basically, here are some examples of 3 tables which have just kind of appeared over random websites, which contain the answer in very nice sort of format. But it's just that if you look into more detail, the problem is somewhat challenging, and I'm going to kind of give you a flavor of the challenges that we faced. So, so one problem is that you need to match the query text with the table's context. You need to know which part of the query to match the row header, look for what is the row header, which is the column header. So you need to kind of first solve the matching task, and then you need to extract the number and its unit. For queries like these, the number itself is useless unless you extract the unit. And unit extraction is a very challenging task. So even for an innocent alphabet like M, there can be two different units, whether you meant meter or million. KT could be kiloton, knot, or carat. And even parsing units is challenging. So slash can be used both to separate, kilometer per hour versus representing alternative units. So we had to deal with all this noise. And that's why structure extraction is so hard for machines. Whereas for us, we won't even blink in parsing out, what this particular string says, okay? And of course, we wanted to exploit the power of redundancy on the web, and we wanted to return answers by creating consensus from multiple sources. Okay, so I'll just take you a bit with this example to give you a flavor of how we attacked this problem. So, so first, we'll continue with this running example of escape velocity of Jupiter, and say we found these 3 tables on the web. So the first thing that we do is noisily match the query string with the row headers and column headers. And because such match is uncertain, we assign probabilities with the match. And then we try to extract the number and the unit. And as I just mentioned, extracting numbers and units is also very challenging. 59.2 versus 59.2, they can represent 2 different things in 2 different regions of the world. And so for extracting units, we created this unit catalog, and then we annotated tables with respect to this catalog of units, and then we would convert all the different variants of units into a standardized unit, and then we would get consensus from all the different occurrences of that factual answer over multiple tables on the web. And then finally, we have the answer, so I'm kind of skipping that. And what we see here, this blue thing is what we call as our collective model, and it gives us higher accuracy than other methods. And this work appeared in the KDD 2014 conference. So basically here is a summary of what I wanted to say is that a lot of the so-called structured information of the world is actually just represented very disrespectfully as unstructured text, and because that information was primarily meant for human consumption, and now though when we are interested in processing data at scale, we would like to automatically extract such information, and my research has been on designing statistical machine learning models and algorithms for aiding such extraction. So this was like in 2014, but in the last 5 years, I have been working on general machine learning problems, and I wanted to give a shout out to you that one problem that I'm specifically working on is how to encode domain knowledge. So I don't want to do machine learning by just learning from examples. I would like to allow humans to provide high-level supervision for building machine learning models. So the kind of high-level supervision which you sort of implicitly encoded, I would like to formalize that and provide a general purpose solution which would work across different disciplines. I work in domain adaptation. I work on several problems around continuous data also, like temporal point processes for various applications. So, so in general, if any of you are interested in applying if you have problems where current deep learning systems' hunger for data is bothering you, I would be interested in talking to you, because I am particularly interested in how to maximize reuse of pre-trained models, how to effectively merge human expertise into building and adapting models more efficiently. Thank you.
Thank you, Professor Sarawagi. So the floor is open for questions again, and we have an open invitation, so please, let's make use of it.
So fascinating talk. So one of the reasons humans learn from very few examples, like my 3-year-old granddaughter, you show her a dog, and after 2 dogs, she will recognize the third creature,
Yes.
which may be twice the size, but as a dog. So that's because there is some hardwiring, there is some intrinsic structure which you alluded to. The interesting thing, though, is that it is generalizable and may set the basis for general AI as opposed to domain specific.
Yes.
And by the end of your talk, you were alluding to it.
Yes.
How might you think? What might be your vision of a general AI that nonetheless has intrinsic structure but learns from a few examples and not zillions?
Actually, so one very important part is going to be reuse. So that's, I mean, one of the reasons I'm interested in more domain adaptation is because I really believe in taking that forward to modular learning. So you learn, like, sort of, in machine learning, people call it curriculum learning, but that has been used in a somewhat narrow sense. Like, there is one task, and you first give simple examples, and then you go into increasingly more complex examples. But what I would like to think of is more like take a big problem and break it up into smaller pieces, and then every new algorithm is in terms of those smaller pieces. And to some extent, when I think about how we did statistical machine learning for information extraction, those pieces, there was, like, when humans did feature engineering, they were using their world knowledge to create those pieces, and thereafter the learning from example part became very simple. Now, what deep learning brought to the table is, hey, you don't need to do feature engineering. We will learn the features. You just give us raw data. But I think that was great. But now, and I don't think we need to throw away whatever deep learning has achieved, but what we need to do is modularize what deep learning does, sort of name them. Look, this part of this image ResNet, this part is recognizing the legs, this part is recognizing the eyes, and this part is recognizing this relationship among the different objects. So I think we need to be more declarative in creating models. In some ways, perhaps maybe because I'm a computer science, we might have to go back to algorithms in the sense that, a task cannot be a black box. You have to declare the variables, you have to declare the procedure, and you have to take the long path. And when you try to take shortcut, in comes something, out goes something. That's when all these problems arise. Sorry, that was a long answer. I don't think there is one good answer, and a lot of people this is a problem which everybody is talking about. So partly maybe I am now the next few things I will be saying will be what I have heard from others so far. So like many people want to now solve this problem by using causality. So we want to create models which are causal. And that reminds me of this quote that, the means is as important as the end, right? So when you're creating causal models, you are sort of making sure you use the right kind of features. You use the right means to do the prediction. So yeah, I don't have one concrete answer. Just
yeah, just carrying on a little bit from that same question. As you start building causal models and so on, often you come up with negative examples. And that's probably because there is some non-monotonicity built into the models going from one to the next model as you improvise the models. Are you looking at non-monotonicity in your modeling?
So I don't think I understand what you mean by that.
Meaning additional information doesn't only improvise the model, it actually makes you look back at the structures that you need to look at.
Yes, yeah.
To reevaluate. So the 3-year-old over here
Yes.
will need to change, from identifying a dog to identifying a cat, and so on and so forth. So those structural elements change because your model is incomplete to start with.
Yes.
And as you build up more features,
Yes.
those features need to be built in and that changes your model in the process. And that would be the kind of non-monotonicity that needs to be
That's
built
right.
into the process.
That would be absolutely required. But then, so when we try to incorporate such thoughts of monotonicity now, when we were working on continuous learning, is that you don't know whether you're breaking things which you had learned in the past. So you might have to revisit some data. And again, maybe that fear we have because our model is to some extent a black box to start with. Whereas if it is more interpretable, then you will not have this fear that, okay, just because now the child, after recognizing a dog, can also understand that a three-legged dog is a limping dog, that kind of refinement, that will require more transparent encoding of the model to start with. So, in general, you cannot, with current black box models, this is very tricky unless you revisit data, because while you're trying to, put whether you want monotonicity or not, that can hurt your previous learning.
Suni, I'm sorry we are all hooking on to the dog example, but I do want to push because the same thought has struck me watching my children. And your black box appeals to me, but I don't quite know. When a child sees you show two dogs and a third much larger one, and the child recognizes that as a dog. All that it shows to me is that human minds have something in common. After all, we could have thought of another society where a big dog is an elephant.
Yes.
The categories are totally different.
That's right.
So this just shows that there is a commonness across human heads.
Yes.
What that commonness is, we don't know. And
Yes.
all you want to do is teach the computer the commonness in our head. There is no innate reason why a big dog is also a dog, but it's the commonness in our heads.
That's right. Yeah, exactly. I think one of the big problems is that currently in machine learning, each task is considered an independent task. Whereas actually in the human mind, all the information that the child learns is interconnected. It's all kept in this one brain. So the representation of word knowledge is what enables a child to sort of generalize from a small dog to a big dog, which current machine learning does not do. Each task is a separate network. So if we could somehow create this one mammoth machine which does all kinds of learning and does the right kind of interconnection, then maybe such generalization would be possible. But technologically, we are not there yet.
Yeah, I was wondering, does it come up that the same information can be extracted by two completely different structures, and when that happens, is the theoretical inclination to say that the data just underdetermines the structure, or is it more plausible to say that there's a kind of isomorphism? It's like centigrade and Fahrenheit, and which carry the same information about how cold or hot it is, but the structures are entirely different. That makes it a completely trivial, because you can have a linear transformation. Or is it rather that it's genuinely underdetermined and there is no linear transformation? They're just two different models or theories.
So it depends on the kind of problem. So if you think of, say, standard recognition kind of tasks, the data in some ways over-determines, right? Because, it's telling you more than what the model outputs. When I take an audio as input and I predict the word, the audio has emotion, it has, so many other things which the model is not predicting. So in some ways, the data is over-determining, and I don't know what you mean by under-determining.
By underdetermined, I just mean that there are two possible structures or explanations for the information that's been extracted.
Yeah, that, of course.
And there's no fact of the matter as to which one is
That's true.
right.
Yeah, that's right. And in fact, so that is the point, that brings us to correlation, to causality. So in fact, the reason maybe why we have so many different explanations or ways to getting at the same prediction is because we are exploiting correlations rather than the true cause. And if you could somehow get to the cause, then maybe you would not have so many paths to the same prediction.
I have a question here.
Yes,
So I think one of the aspects which we need to consider in machine learning
yes,
is about logic and reasoning.
yes,
So for example, if we take the case of the address parsing problem, we as humans probably look at that and even subconsciously figure out that, hey, this can't be the name of a street, it must be something else. And the overall parsing tends to make sense.
yes.
So what are your thoughts on figuring out logic and reasoning in
Yeah,
machine learning?
actually, that's a very interesting problem. And in fact, right now, I said I'm not working on the address problem, but I have been dragged into working on it. I am kind of doing some collaboration with Flipkart on, there we are trying to bring in some logic. Actually, earlier, when we were working on this CRF-based models, we are very scared of non-convex optimization problems. Now we are not, thanks to deep learning. So when you bring in logic and all kinds of transition, all this tangential auxiliary information, then your learning problem becomes non-convex. And so now we are trying to bring in all these other,
I have a last question.
Yes.
Understanding how the brain works and the logic circuits in the brain work will help you develop better algorithms for machine learning. Can machines learn to mimic the way the brain works so that this challenge of a child looking at a dog and recognizing something bigger as a dog can be solved in a short period of time?
So, actually, sorry, I don't know much about this.
No, I'm
program.
asking.
I can give you a flow.
No, I'm asking this question because one of the intent of this symposium is to look at multi-dimensional research and try to find the areas where they interact. Now you are talking about machine learning, data structures. One of the best example is how the human mind works.
I mean,
So if you link it to brain research, will you find new ways of doing things better?
I mean, of course, I thought this question is rhetorical. Of course, it can help you. Like, if I understood how brain works, and if I could imitate that perfectly, then all these loopholes of machine learning that we currently hear of will go away. And of course, it's going to help. It's just, I don't know. I cannot give a more intelligent answer than that. So I thought, I just can say, it will help, but I have not thought about it deeply enough, and I don't understand that area enough to give you any intelligent comment on that.